Okay, are we live? Oh my God, we're live from New York. It's Saturday morning. Okay. So I think we should just get going. So I think I have no announcements for the first time in history. It's with great pleasure that I introduce Roberta Bonacina, who will speak about joint work with Benedikt, Ahrens, and Nicolai Kraus on syntax for two-level type theory.
Thank you very much. So let me share the full screen. You know that the univalence axiom is very useful in homotopy type theory. It allows to identify isomorphic things, and so it is possible to transport properties between those isomorphic objects using explicit identifications. But, this may be useful in many cases, but it also gives rise to problems. Indeed, there are notions, for example, strict equality, which are not homotopy invariant, and so it becomes hard to express internally those notions. Sometimes it's possible to rephrase those notions and then express them in HoTT, but it's not always possible. And one example of this situation are the semi-simplicial types. So Vygotsky tried the first attempt to solve this problem, defining his homotopy type system. And this system contains two equality types. We have the usual propositional equality, and we have exact equality, which is the definitional equality, but internalized and with some other assumptions. Here we have that this second equality, exact equality, allows to have, in a sense, another level of type theory. And this second level can be used to reason about HoTT and not inside it, as we do with the usual equality. So, two-level type theory, which is the system which we are studying, is a variant of a homotopy type system. And we don't have only two equalities, but we have two different levels of types. So we have two type theories which share a common core. For example, they share the context, and we have an outer system, an outer level, which are those types. For example, this B, called just as types, and an inner level, this A, which is distinguished by the outer one with this label O. We have that in the outer level, propositional equality is strict. So it has function extensionality and the uniqueness of identity proofs, while the inner universes are univalent. So we have that the inner level represents homotopy type theory, and the outer level is a strict system which allows to study homotopy type theory, having strict equality. So those two levels are related. They have the same context, and there is a map from inner types into outer types. This conversion map C, which, as I said, maps inner types into outer types, and such that if we extend the context gamma, if we have that A is an inner type in context gamma, we have that we can indifferently extend the context gamma with the A or C of A. We will obtain, in any case, the same context. Well, we have that our system is defined semantically in the original paper, and it is seen as the initial object of a certain category of models, which is based on categories with families and extends the usual notion of category with families. What we are doing is, well, we defined a syntax in details, and we are working to show that the syntactic model of our syntax is initial in the category of models. So let us see a few features of the syntax. We have, as I said, a conversion function, C. If A is an inner type, then C of A is an outer type. And, well, this was present also in the original paper, but we also introduce another conversion map, C prime, which maps terms of inner universes into terms of outer universes. And as I said, we have that if A is an inner type, then the context gamma x of type A is equal to the context gamma y of type C of A, obtained using the conversion function. To formalize this fact, we had to introduce a notion of equality between contexts. And, well, we have that, of course, this equality is an equivalence relation. And we also have this property. So if the two types A and B are equal, it happens both for inner and outer types, then the context extended with A or with B are equal. So some other rules, well, we have that as we can infer from also from those rules, our universes are Tarski-style universes, and they are seen as uniform constructions. So we have a map L, which maps terms of universes into types, and we have it both for inner and outer terms of universes. So the terms of outer universes will become outer types, and the terms of inner universes will become inner types. And we also have two lifting maps, lift and lift O, such that lift maps terms of outer universe of if A is a term of the outer universe UI, then lift I of A will be a term of the universe UI plus 1. And again, the same happens for inner universes. What we have is that all those operators commute. So we have that if A is a term of type UI, then EL I plus 1 applied to lift I of A will be equal to EL I of A. And we have also that if A is a term of an inner universe, then it will be the same applying to A C of ELIO and ELI of C prime. And again, we will have that lift I of C prime of A is judgmentally equal to C prime of lift IO of A. So those were some characteristic of the syntax, which arise some issues which are still open for us. So we introduced those maps, C, C prime, lift, and EL, and we are wondering if some of them can or should be made silent, because this may be better and for the construction of a potential proof assistant. And well, we want to avoid cumulativity. Indeed, we use Tarski universes because it may create difficulties with typing. But we have that the rule ulift. So this one is a way to recover, in a sense, the useful properties of cumulativity. And we're wondering which are the models that we can have having this rule. And again, about models, we have an open issue also with this other rule, this equivalence of context, because it may be too strict. We have that with these rules, different terms. Sorry, a term may be two different types, which may be useful because inner and outer types have to be related in some sense, but it may again create problems with potential proof assistance. So this was the syntax, and we have that a one-level model is a category of families enriched with some maps to interpret our maps, EL, lift, and so on, and to interpret the types. And a two-level model consists again in a category, E, then a model which is the outer level. So it is a category with family E, TY, TM, and 1 with a certain set of typeformers. We will have that we have the usual inductive types, and here equality is univalent. Here the equality is strict. Then we will have another model, MO, with the same base category and other shifts TYO, TMO, and the same terminal object 1. Here the typeformers are T0, and again we have the usual inductive types, but here equality is univalent. And then we have a conversion morphism C, which goes from MO to M, so from the inner level to the outer one. C is the identity on category E, on the category E, but we have that for each gamma in E and for each A in TYO of gamma, gamma.A is equal to gamma.C of A. So the two context extensions are the same. They give rise to the same object in the category. So to prove initiality, we have to construct at first the syntactic model. Here, the syntactic two-level model can be obtained by constructing a two-level structure from the syntactic category with families. We define at first the syntactic category S. Here, the objects are the contexts, and the morphisms from to context gamma to delta, where gamma is x1 of type A1 up to xn of type AN, and delta is y1 of type B1 up to ym of type BM. Well, a map is a sequence T1, Tm, such that for each I, we have that gamma proves that Ti is of type Bi with the previous T's substituted to the Y's. Then we define the Proshev Ty as such that Ty of gamma is the set of the types A such that gamma proves that A is a type. Then the Tm is such that Tm of gamma and A is the set of the terms of type big A in context gamma. Then we have that the terminal object of our category is the empty context. And to extend a context gamma, we have that the extended context is gamma x of type A, and the projection map PA is the sequence of the variables in gamma, and the term QA. So the other projection is the variable x of type A, so the one of the type with which we extend gamma. We have that this S is a category, but it's not a category with families. So to obtain a category with families, we quotient S according to internal equality. And the equivalence relation is generated by those relations. So two contexts are equivalent if they are equal. Two morphisms are from gamma to delta are equivalent if the two sequences are equivalent if they are pointwise equal. So if the terms in the sequence are pointwise equal. Then two types in a context gamma are equivalent if it's possible to prove that the two types are equal in context gamma. And again, two terms of type A in context gamma are equivalent if gamma proves that the two terms are equal terms of type A. So we have that all the quotients of the previous slide are well defined by the structural rules of the system. So we defined a suitable notion of morphisms between models. And now we are working to prove that our syntactic category with family S is initial in the category of models. So if we take M as a model for level type theory, we want to prove that there is a morphism F of M from S to M, and that this morphism is the unique one from S to M. So in summary, we have defined in details a syntax for the system to level type theory, which was only sketched in the original work on introducing this system. I've showed you only the most important rules for it. We define a notion of model for this system and a notion of morphism between models. We define the syntactic model and prove that it is indeed a model. Now, we want to prove the initiality result, and to do so, we need to show that there is a canonical morphism from the syntactic model to another fixed model M, and then prove that this morphism is unique. And our long-term goal is to develop the basis for a proof assistant which implements level type theory. Those are the references, and yeah, this was it.
All right, thank you very much. So applause in the chat is most welcome, and anyone who has a question should feel free to raise their hand, and you will be admitted to the live feed. See a lot of applause going up. But yeah, I'll wait a little bit for all the raised hands, since I think it's a highly non-trivial thing to do. Oh, there's a question. Okay, let's. Okay, we're patiently waiting. But maybe the talk was just so clear that there are no questions. For the first time, we're not out of time. we're still within time. Okay. Here's what I'm gonna do. I'm gonna perhaps close this area. There's some button that allows me to do that, and a discussion can continue in a smaller group, and we can also get ready for the next talk. So thanks again, Roberta, and we'll be moving to the next talk or continuing the discussion. So you will get a prompt to do either of those things.
You have a link to go to the discussion area in the chat. So you can click there, you go to the discussion.
Thank you.
Thank you, Roberta.
And